Hello, I'm Ninon Burgos. I'm a researcher at the Paris Brain Institute. And so during this lecture, I'll show you how to design and validate classification pipelines for brain diseases to ensure an objective and reproducible evaluation. As you might have seen from the other talks of this course, the analysis pipelines used for individual patient classification or regression can vary, but they often include 4 elements. The first element is a training dataset with a sufficient number of subjects with well-characterized clinical properties. This is necessary to reliably express the disease effects against the noise of intersubject variability. The second element includes data processing to extract features and optionally dimensionality reduction. You might, for example, want to process MR images to obtain cortical thickness measurements. The third element consists in training and optimizing your model. At this step, you select a supervised algorithm, for example, a support vector machine or a random forest, and the parameters of the model are optimized to maximally discriminate one group from another on the basis of the training dataset, usually using cross-validation. And finally, the model can be applied to independent test data that have been preprocessed in the same way as the training data. When using a deep learning classifier, such as convolutional neural networks, the elements remain pretty much the same. The main difference is that instead of extracting handcrafted features beforehand, this step will be done automatically as part of the training of the model and its optimization. This talk will focus on the computer-aided diagnosis of Alzheimer's disease, but the principles can be applied to other tasks and disorders. So let's briefly talk about Alzheimer's. Alzheimer's disease is the most common cause of dementia. It is a disorder caused by abnormal brain changes that trigger decline in cognitive abilities that are severe enough to impair daily life. It affects behaviors, feelings, and relationships. And Alzheimer's is a progressive disease. Cognitively normal subjects can start with mild cognitive impairments that may or may not progress to dementia. The diagnosis of Alzheimer's disease mainly relies on clinical examination and on cognitive tests, but imaging can also play an important role. You can observe neuronal loss on structural MRI with an atrophy of structures such as the hippocampi or an expansion of the ventricles. Neuronal degenerations can also be observed on metabolic PET images, and other imaging modalities as well as CSF can provide useful biomarkers. If we take Alzheimer's disease as a use case, this type of pipelines can be used to perform classification tasks. For example, clinical diagnosis classification, like differentiating cognitively normal subjects and patients with Alzheimer's disease, or more predictive tasks of the evolution from the prodromal stage of the disease. These pipelines can also be used to perform regression tasks, for example, to predict the time of onset or a future clinical score. Developing tools for Alzheimer's disease diagnosis and prognosis using machine learning and more recently deep learning has been a very active field of research. However, the classification performance is difficult to compare across studies due to variations in training and test sets, imaging modalities, image processing pipelines, feature extraction, classification algorithms, cross-validation procedures, and reported evaluation metrics. And because these works are almost impossible to compare, it is very difficult to conclude which methods perform the best. And so the practical impact of this work has remained very limited. In this talk, I'll explain how to design and validate pattern recognition for clinical application in brain diseases by answering several questions. We will first see where to find data for training and testing and how to best organize them. We'll then see how to preprocess and extract features from images. Now that we are ready to play with machine learning, we'll see different classifiers can be selected, that different cross-validations can be implemented, and that some tasks may be more relevant than others. Finally, we'll see what is the influence of some of these choices on the classification performance. Our support is Clinica. Clinica is an open source software platform for clinical neuroimaging studies that is written in Python and uses NiPipe for pipelining. It can take as inputs several modalities, such as MRI and PETs. Clinica provides complex processing pipelines that involve the combinations of different software packages, such as SPM or FreeSurfer. Once the images have been processed, they can be used as inputs of statistics and machine learning analysis approaches that relies on libraries such as scikit-learn and PyTorch. The input data are organized following the brain imaging data structure or BIT format. The outputs follow the Clinica process structure or CAPS format that shares BITS philosophy. And as not all datasets are organized in bits, Clinica also provides tools to convert publicly available datasets to bits. So let's start really at the beginning, finding your data. So to build your train and test sets, you can rely on public datasets. For dementia, several are available through the Image and Data Archive websites, such as ADNI or ABLE, but you can find others on independent platforms such as Oasis. Of course, you can find publicly available datasets for other conditions. Once you've downloaded your data, you need to organize them, as it is simply not pleasant and efficient to work with something looking like that. You'll prefer this type of organization and format that corresponds to the brain imaging data structure or BITS. The adoption of a common standard to describe data and its organization on your disk can provide multiple benefits, such as minimized curation, error reduction, or optimized usage of data analysis software. Because reorganizing datasets to follow the BITS format can be a bit painful, Clinica provides converters for different publicly available datasets, namely ADNI, ABLE, Oasis, and NIFD. Now that all is well organized, we can start looking at the images. Depending on the dataset, several modalities may be available. For ADNI, you'll have, for example, anatomical and diffusion MRI, but also PET with different tracers. In the following, we'll focus on anatomical MRI as it is the most common one. So images usually don't go straight from the scanner to the classifier. And so depending on the type of classifier, different preprocessing and feature extraction steps may be necessary to achieve acceptable performance. MR images can be corrupted by a low frequency and smooth signal that is caused by magnetic field inhomogeneities, and you may need to correct these intensity inhomogeneities. You will also probably want to finally register your image to a template so that voxels in corresponding positions contain comparable information across subjects. To improve matching between your image and the templates, you may want to perform non-rigid registration. Skull stripping could also be useful to prevent extracranial tissues from interfering with your analysis. These steps should be enough for the use of deep learning algorithms, but for traditional machine learning, it might be necessary to extract specific features. In our Alzheimer's context, it could be interesting to segment gray matter to assess atrophy. And also to limit the number of features, a solution could be to compute regional averages. These different steps can be performed using different tools developed by the community, such as SPM, FSL, FreeSurfer, or ANTS. But to avoid having to juggle between different tools, several pipelines combining them have been implemented in Clinica. You can thus pre-process anatomical MR images, but also diffusion-weighted and PET images. Okay, so now that we have pre-processed our images, it's time to choose a classifiers. And you can choose between many classifiers, such as the linear support vector machine, L2 logistic regression, or random forest. The linear SVM can be a good option when dealing with many features, which happens when you use wall images. And for example, random forest can be a good option when mixing different types of features, such as clinical and imaging features. If you go for deep learning, convolutional neural networks are the most commonly used for image classification. They can take as input wall 3D volumes, but also 3D patches or 2D slices. Rigorous validation is essential to objectively assess the performance of a classification framework. It is good practice to have two nested loops, an outer loop that evaluates the classification performance, and an inner loop that is used to optimize the hyperparameters of the model. Different cross-validation strategies can be implemented, such as the K-fold, where the different folds won't be contiguous, or the repeated holdout, where there could be overlaps. But I won't go into more detail, as cross-validation is covered by Pradeep in another lecture of this course. But I'd like to draw your attention on a major source of evaluation bias, which is data leakage. Data leakage refers to the use of test data in any part of the training process. It can be difficult to detect, especially for deep learning approaches, as they can be complex and very flexible. And in a review study that we performed, we identified 4 main causes of data leakage. Late split occurs when procedures such as data augmentation, feature selection, or autoencoder pre-training are performed before splitting into the training, validation, and test sets. Transfer learning can result in data leakage when the source and target domains overlap. This is, for example, the case when a network pre-trained on the cognitively normal versus Alzheimer's disease task is used to initialize a network for the cognitively normal versus mild cognitive impairment task, and that the cognitively normal subjects in the training or validation set of the source task are also in the test sets of the target task. Not splitting the dataset at the subject level when defining the training, validation, and test sets can result in data from some subjects to appear in several sets. This problem can occur when patches and slices are extracted from a 3D image, or when images of the same subjects are available at multiple time points. And I could have started with the simple absence of an independent test sets. And the test set really should only be used to evaluate the final performance of the classifiers, not to choose the training hyperparameters. For that, you need to use a separate validation sets to optimize your hyperparameters. So now let's look at the task that can be of interest. If we take the example of the ADNI datasets, you have several diagnosis groups. Participants can be labeled as cognitively normal, CM, mild cognitive impairment, MCI, or Alzheimer's disease, AD. Even though its clinical relevance is limited, differentiating patients with Alzheimer's disease from cognitively normal subjects is the most widely addressed task, and it can be useful mainly when developing methods. Distinguishing MCI subjects that will progress to Alzheimer's from those that will remain stable would be more interesting. It would allow predicting the group of subjects that will likely develop the disease. But for that, we need to define new labels. We label as stable MCI, so SMCI, subjects who were diagnosed as MCI at baseline, were followed during a certain time. Here it's at least 36 months. And who did not progress to Alzheimer's disease during this period. Similarly, we label as progressive MCI subjects who were diagnosed as MCI at baseline, were followed during 36 months and progressed to AD. And so the stable versus MCI task, stable versus progressive MCI task can thus be seen as a really predictive task of the evolution. Now that we have all the ingredients of our analysis pipelines, we can really study how the choices you make in terms of, for example, features, classifier, or cross-validation impacts the classification performance. Here in this work, we used, for example, regional features extracted from T1 so anatomical MR images of ADNI participants to compare the performance of 3 different classifiers. And you can see that both the linear SVM and logistic regression with L2 regularization models, they lead to similar balanced accuracies, and which are higher than the ones obtained with random forest. Here we study the influence of the type of features. So we compare the balance accuracies obtained for voxel and regional features that were extracted from T1 images of ADNI participants when using a linear SVM classifier. And you can see from the result that there is no notable differences between the mean balance accuracies obtained using voxel or regional features. Until now, we focused on ADNI, but we also want to know whether the results obtained generalize well across datasets. And so to do that, we are going to use images from 2 other studies, ABLE and OASIS. We focus on the task cognitively normal versus Alzheimer's disease and use 70 subjects per class for all datasets to have a fair comparison. When the training and testing are performed within datasets, you can observe that ADNI and ABLE reach similar accuracies, while the accuracy is lower for OASIS. This can be explained by the difference in the label definition. In OASIS, the Alzheimer's disease label, AD label, comprises both patients with mild cognitive impairment and Alzheimer's disease, and so the task is more difficult. Then you can see that when training on ADNI and testing on ABLE and OASIS, the accuracies stay like the same or slightly increase. And so this means that the classifiers trained on ADNI generalize well to other datasets. Previously, the experiments were performed in the traditional machine learning context, but we can perform similar experiments in a deep learning context. In particular, we are going to study the influence of the preprocessing type of the network architecture on the classification performance. We first study the influence of the type of preprocessing using a 3D subject CNN. We compare a minimal preprocessing that comprises bias field correction and affine registration to a template with a more extensive preprocessing that comprises bias field correction, non-rigid registration to a template, and scale stripping. And you can see that there is no notable differences between the mean balance accuracy obtained using the 2 preprocessing strategies. So using this minimal preprocessing, we then study the influence of the CNN architecture. We compare networks taking whole 3D volumes 3D patches covering the whole brain or a specific region, here the hippocampi, and 2D slices as inputs. In general, the 3D subject level and 3D patch level approaches provided approximately the same level of performance, and the 2D slice approach was less efficient. And we can hypothesize that this is because the spatial information is not adequately modeled by the 2D slice approach. We also studied the generalization across datasets in the context of deep learning. We trained a 3D subject level CNN on ADNI and tested it on independent ADNI, ABLE, and OASIS datasets. Overall, the model generalized well to ADNI for both the CN versus AD and stable versus progressive MCI, and to ABLE only for the CN versus AD task. But you can see that the model doesn't generalize well to the stable versus progressive MCI task for ABLE. It could be because MCI participants from ABLE are substantially older than those of ADNI, which is not the case for the AD and CN participants. And as for the traditional machine learning approaches, and so for the same reason, the accuracy is lower for OASIS. One interesting question is whether deep learning could perform better than conventional machine learning methods for AD classification. And so we compared the deep learning and machine learning approaches that led to the highest accuracy, so which are the 3D subject level CNN and linear SVM. In this study, you can see that the SVM is at least as good as the CNN. So maybe I can make a few remarks. It is not excluded that more sophisticated convolutional machine learning methods could provide even higher performance. And similarly, more sophisticated deep learning architecture could outperform conventional machine learning methods. These are really just like the results of this particular study. And also the performance of deep learning approaches might improve when training on larger datasets. So during this presentation, we've seen the different elements that contribute to make evaluation of machine learning and deep learning approaches in Alzheimer's disease more reproducible and more objective. There are several key components that guarantee reproducible research, which is the ability to reproduce results based on the same data and experimental procedures. And these are data sharing, and if the data cannot be redistributed, then tools that automatically convert datasets into community standards. Also storing of data using community standards, fully automatic data manipulation, and sharing of code. The objective evaluation of a new approach, for example, a new feature extraction methods or classification algorithm, requires testing the specific component without changing the others. This is possible by using standard approaches for preprocessing and feature extraction and standard classification tools that constitute a set of baseline approaches against which new methods can easily be compared. And of course, rigorous validation is needed. So here are references for the ADML and ADDL frameworks that we developed for the reproducible evaluation of Alzheimer's disease classification experiments. They rely on the Clinica software platform. The framework comprised tools to automatically convert publicly available datasets into the bit standards, and a modular set of image preprocessing pipelines, classification algorithms, and evaluation procedures dedicated to both machine learning and deep learning. So with that, I would like to thank you for your attention, and I would like to thank the people in the team that who work on this project and all the contributors of Clinica. Thank you.
First, I'd like to thank Christophe and Janaina for organizing this educational course. As you all might notice, this educational course covers a broad range of topics across both classical machine learning and deep learning. For my portion of the course, I'd like to explain our motivation for why this course is not fully devoted to deep learning. Without a doubt, deep learning has revolutionized machine learning. Deep neural networks have achieved state-of-the-art performance in many fields. For example, DeepMind's AlphaGo is able to beat the world's best human players in the game of Go. And in computer vision, object detection accuracies have skyrocketed in the past decade. The orange and yellow lines show the Pascal Visual Object Class challenge. The goal of these challenges is to test the ability of computer vision algorithms to recognize objects in images. In these data sets, accuracy has dramatically increased from 34% in 2014 to 84% in 2018. However, despite deep learning's dominance in many fields, classical machine learning remains competitive in some domains. For example, Google's 2018 paper shows that deep learning with electronic health records can predict inpatient mortality with 95% accuracy. However, if we look at the confidence interval, we see that logistic regression performed just as well. As another example, here's a Nature paper that uses a deep neural network with 13,000 parameters to predict aftershock patterns following large earthquakes. The authors achieve an area under the curve of 0.847. However, others have pointed out that they can achieve the same AUC if they use logistic regression with two input parameters. As we go back and forth between the two ROC curves, we see that the performance was virtually identical between the two approaches. What about neuroscience? That's what we're interested in today. Today, we want to discuss the utility of deep learning in neuroscience. First of all, it is important to divide deep learning applications into two very different types. The first type is using deep neural networks as models of the brain. For example, given that deep convolutional neural networks can perform computer vision tasks very well, perhaps they can provide insights into the neuromechanisms of visual perception in humans and animals. Indeed, deep neural networks have provided rich insights into the mechanisms of many different brain functions, such as vision, auditory perception, reinforcement learning, navigation, task performance, and so on. The second type of application is using deep learning as a tool to analyze brain data. Examples will include lesion tumor segmentation, image modality transfer, image restoration, and behavioral disease prediction. Today, we'll focus on this second type of application. In particular, we want to discuss whether deep learning has proven to be more accurate than traditional machine learning techniques. For this question, we can consider two lines of evidence. First is the evidence from competitions or challenges. In these competitions, teams are given training data with no access to the targets or labels they have to predict from the test set. Teams would then train and tune their models on the training data and then submit their prediction for the test set. Because teams do not have access to the true targets or labels in the test set, therefore they cannot consciously or unconsciously cheat by looking at the test data. The 2019 PAC challenge requires participants to predict brain age using anatomical T1 images. The winner uses deep neural networks, so that is one win for deep learning. What about the 2019 ABCD prediction challenge? This challenge requires participants to predict the fluid intelligence of 9 to 10-year-old children using anatomical T1 data. However, this time, the winner uses kernel regression rather than deep learning. Overall, for anatomical and lesion segmentation challenges, deep learning has a consistent winning track record. However, for predicting behavior such as fluid intelligence, demographics, or diseases, deep learning has a mixed track record up till now. As I was saying, the winning algorithm for PAC brain age prediction uses deep learning, but the winners for the ABCD Fluid Intelligence Prediction and the TAPO 2019 Challenge both use classical approaches such as clonal regression or XGBoost. One problem with using evidence from competitions is that the winner is usually based on the point estimate of prediction accuracy. For example, the winning team might only be better than the second best team by 0.0001%. So in that scenario, the winner might actually not be statistically better than the second best team. Therefore, looking at evidence from benchmarking studies will also be quite important. In a recent study from my lab, my student He Tong utilized about 10,000 subjects from the UK Biobank and the Human Connectome Project. He used resting state function connectivity to predict a wide range of behavioral and demographics measures. He compared kernel-rich regression and 3 deep neural networks, fully connected feed-forward neural network, BrainNet CNN, and graph convolutional neural networks. The fully connected feed-forward neural network is just a generic neural network, while the BrainNet CNN and graph convolutional neural networks have been developed for graph data, such as functional connectivity data. Therefore, we might expect BrainNet CNN and graph convolutional neural networks to perform better than the fully connected feed-forward neural networks. Here's the result for predicting fluid intelligence in the UK Biobank. The y-axis is prediction accuracy measured using Pearson's correlation. The x-axis shows kernel-rich regression, KRR, fully connected neural network, FNN, BrainNet CNN, BNet CNN is BrainNet CNN, and graph convolutional neural network, GCNN. He Tong found that the prediction accuracies were basically identical across all approaches. In the case of sex prediction, He Tong again found that there was no statistical difference among the different approaches. So overall, across the 2 data sets and all the non-imaging measures he predicted, the prediction performance was highly similar between kernel regression and deep neural networks. He Tong then varied the number of training subjects from 100 to 7,000. X-axis is the number of training subjects. Y-axis is the fluid intelligence accuracy in the test set. He found that as the number of training subjects increase, the prediction performance keep increasing. However, there's basically no difference between kernel regression and the other 3 deep learning approaches. Overall, this is quite surprising because BrainNet CNN and graph convolution neural network should be great for connectomics data. But we found that the generic fully connected neural network and kernel regression perform just as well. Now, it is possible that He Tong is not so good at tuning deep neural networks. So here's a second benchmarking study from Steve Smith group using 14,000 subjects, again from the UK Biobank and Human Connectome Project, and also from Abide and the ACPI datasets. So the authors used resting state function connectivity to predict non-imaging measures such as age, sex, and fluid intelligence. They also proposed their own 2D recurrent convolution neural network. So what did the authors find? The authors concluded that their carefully designed deep learning-based architecture, 2D recurrent convolution neural network, can be a very valuable tool for analyzing functional connectivity. However, ElasticNet probably performs better at present overall. So what could be the reason for this? Why is deep learning really crushing it in some areas, such as computer vision and natural language processing, but not the clear winner in these benchmarking studies? An interesting preprint from Danilo Bisdock group proposes that perhaps it is somehow more difficult to exploit nonlinearity in MRI data when it comes to predicting variables such as age, fluid intelligence, and sex. Let's consider a standard computer vision dataset, MNIST. Y-axis is the prediction accuracy. X-axis is the training sample that goes from 100 to 8,000. Here's the prediction accuracies for different algorithms. We see that the prediction accuracies get better with larger sample size. The pink, orange, red lines correspond to classical linear algorithms like linear SVM. The green lines correspond to classical nonlinear methods, such as kernel SVM. We see that the green lines are above the red-orange lines, so classical nonlinear methods outperform classical linear methods in this data set. Finally, the blue lines correspond to deep neural networks, such as convolutional neural networks. We see that the blue lines are above the green lines, so deep neural networks outperform classical nonlinear methods in this data set. Overall, we see that in this standard computer vision data set, there is a clear gain in accuracies as we go from classical linear to classical nonlinear to deep neural networks. What if we repeat the same analysis for NeuroImaging data? Here's the result for predicting age and sex using anatomical T1. We see that classical linear, classical nonlinear, and deep neural networks exhibit no difference in performance. This is quite interesting because this suggests that perhaps when predicting behavior or demographics using anatomical T1, it is difficult to exploit nonlinearity in the data. I want to be clear that I'm not saying deep learning is not useful. In fact, my group also uses deep learning for some problems. And I would like to share with you our experience on developing a deep neural network for the TAPO challenge. So this work is spearheaded by my student Ming. So the TAPO challenge is set up as follows. For each subject, we're given 23 multimodal biomarkers at one or more time points. And our goal is to predict the cognitive scores, brain atrophy, and clinical diagnosis of the subject for every month indefinitely into the future. Of course, even though we would like to predict indefinitely into the future, the evaluation can only be done for available time points, which is about, if we split the data in half, we get about 5 years in the ADNI data set. The challenge is that there are lots of missing data, right? So for example, while the clinical dementia rating scale is available at 70% of the time points, tau PET is available only in 16% of the time point. Most studies simply assume all data are present, right? So they throw away subjects with missing data. But this means throwing away a lot of data. In addition, missing data is very common in real life. So if we want our tool to be useful in real life, it has to deal with missing data. Therefore, Ming developed a deep recurrent neural network algorithm that can handle missing data. Because this is longitudinal data, we felt that recurrent neural networks should be perfect for this task because the recurrent neural network should be able to encode basically long-term patterns in the data. So we perform tenfold nested cross-validation, and we evaluate prediction performance for clinical diagnosis, ventricular volume, and cognition. The results are consistent across all measures, so I'll basically just show you the clinical diagnosis results. X-axis is the number of years we're predicting into the future. Y-axis is the prediction accuracies, so higher the better. The green bars are the constant baseline. So this baseline is basically predicting the last observed clinical diagnosis. So this assumes that the diagnosis of the person does not change over time. We see that accuracy decreases the further we predict into the future. Furthermore, the error bars increase as we go into the future, right? Because we have less and less data. An important point to note is that we get about 80% accuracy, even 5 years in the future. So when you read about studies predicting future health outcomes, the accuracies are meaningless without a proper baseline. The blue bars are our approach. We see that the blue bars are higher than the green bars, so our recurrent neural network performs better than the constant baseline. And 5 years into the future, we can achieve more than 90% accuracy. We also compare with other baseline approaches, and our recurrent neural networks still performs the best. So how did our recurrent neural network perform in the TAPO challenge? So the TAPO challenge allows us to test our model on completely unseen data from ADNI. Because anyone can sign up to access the ADNI data, so what the challenge did is that we have to predict future data that have not been released yet. So we actually submitted our prediction in 2017, but we only know the results in 2019. In the original challenge, our team was in the 5th place, but we improved our algorithm, so we're currently ranked 2nd and 3rd out of 63 entries. But the punchline is this. The winning algorithm is actually XGBoost, right? Therefore, even though Ming's deep neural network was able to beat many other algorithms, we still lost to a non-deep machine learning algorithm. Again, I want to emphasize that deep learning will play an important role in analyzing MRI data, but I think we have to be careful about the hype. In particular, I want to share with you some things I look out for when I read MRI papers that utilize deep learning to predict behavior or disease or demographics. First, if we replace deep learning with logistic regression in the paper, is the paper still interesting? For example, would the earthquake paper be published in Nature if they use logistic regression and achieve the same prediction performance? Probably not. Deep learning is a very big umbrella term comprising many different architectures and algorithms. When I read a paper, I like to think about why does this paper use this particular deep neural network? Do the inductive biases of the deep neural network fit the problem the authors are trying to solve? The second important point is sample size. As Gael showed in his 2018 paper, even with 100 subjects, the estimated prediction accuracy can have big error bars of plus minus 10%. You can see plus minus 10%. So this means that if we perform cross-validation with 100 subjects and we obtain an accuracy of 80%, then the true prediction accuracy might be as low as 70% or as high as 90%. Therefore, in my opinion, when using MRI to predict behavior, disease, or demographics, studies should use much more than 100 subjects to be credible. Finally, there are many hyperparameters in deep neural networks. Linear regression has one hyperparameter. Kernel regression has one or two hyperparameters, depending on the kernel. If the choice of kernel is considered as a hyperparameter, then kernel regression will have 3 hyperparameters. On the other hand, deep neural networks have many, many more hyperparameters, easily more than 10. Therefore, we have to be extra careful about how to tune the hyperparameters. Basically, the hyperparameter tuning should not make use of the test data at all. If not, we risk overfitting to the data. So when I read a deep learning paper, I usually check how the authors optimize the hyperparameters. If the authors say they manually tune the hyperparameters and they use K-fold cross-validation, then to me, that's a very big problem because information from tuning using one portion of the data will leak to another portion of the data because the person who is manually tuning the hyperparameters cannot forget her previous tuning experience. The only legitimate way to use inner loop nested cross-validation is if all hyperparameters are tuned automatically. But as you know, with deep learning, this is very difficult because there's so many hyperparameters. If the authors use an algorithm to automatically tune all their hyperparameters, it would take a very long time because they need to repeat the hyperparameter tuning process K times for a K-fold cross-validation scheme. In practice, when I talk to some people, they tell me that they use an algorithm to tune a small number of hyperparameters, with the remaining hyperparameters being manually set to generic values. To tell the truth, I'm a bit skeptical when I hear that. In my opinion, the cleanest way is to utilize the training validation test scheme rather than the inner loop nested cross-validation scheme when it comes to training deep neural networks. So in this scheme, we divide the data into training, validation, and test set. We use the training set to train the model and the validation set to tune the hyperparameters and to improve the algorithm. We only use the test set once, which is to perform the final performance evaluation. To summarize, deep learning has revolutionized machine learning. As models of the brain, deep neural networks have provided important new insights. As tools for analyzing brain data, I believe deep learning is very promising. Deep learning is very good in image processing type problems, such as anatomical lesion segmentation or image segmentation. However, when it comes to predicting behavior, age, or disease using anatomical T1 or functional MRI, I think the advantage of deep learning is still unclear. In terms of competition, deep learning has not dominated the field. Of course, things could change tomorrow. In the case of benchmarking, 3 recent studies have suggested that deep learning and classical approaches can achieve similar performance. However, I do want to note that another recent benchmarking study from Vince Calhoun's group have suggested that these previous benchmarking studies are perhaps not making the best use of deep learning. I'd like to thank all my funding sources, and of course, my lab and my collaborators. Before I end, I'd like to advertise the Women in Neuroscience repository. The aim of this website is to help identify and recommend female neuroscientists for conferences, symposia, or collaborations. So if you enjoy a talk from a female scientist, please go to the website and submit your recommendation. I have done it multiple times before, and it will not take more than a few minutes. Thank you.